Let's wait for a couple of minutes, and after that I will start. Okay, let me start. So, introducing, I'm Sujatra Bhattacharya. I'm a PhD student at Center for Atmospheric and Oceanic Sciences at Indian Institute of Science. So, I'm currently in third year of my PhD, and most widely, as you can see, it is atmospheric and oceanic sciences. There, you use these linear regressions or multilinear regressions and all polynomial regressions. So these are widely used in my field. So uh, I will try to uh, give you as much as I can by solving different problems and giving the context. So let me just open this. I think it is visible. So today my plan is to start with, as you know, in the course structure, the first thing is that you have simple linear regression. So I will do that simple linear regression today. But before that, I just wanted to give some preliminary requisites which are there for the course, like the statistical distributions, like PD. What is PDA? The continuous PD. Just one liner definition, just the mathematical function. Those things I will just start. What is an estimator? Because these estimators and all these things. Yeah. So these estimators and those distributions like normal distributions, t distributions. So how you can create those distributions? Like if you have looked at what you call as your lecture series, which is already being provided to you. So there you will find that chi-square distribution is there. So what are those distributions? How we can create those distributions? I will just give you a brief of that in the beginning, and then once we are fine with those, we will go towards the simple linear regression because from now onwards, any week you go of this particular course, you will be using those distributions. So just a basic starting point, maybe for half an hour or 40 minutes, and after that we will try the simple linear regression. We will derive something, not everything. Everything is already been derived in the lectures, so I don't want to derive everything. After that, we will go towards problem solving. So that is the main idea, so that you can solve the assignment question. So I will be focusing only on the week 1 lectures, that is ABC, which is there in the simple linear regression. Fine. So this is my core plan today. Uh, so I will start with, so that I just close my camera because I think there is some, it might be some issue with the internet. So I am just closing it for some time. Okay. So I'm sure you are seeing my screen. You're able to see my screen and I'm audible also. Fine. So I will start with some basics of what you call as the statistics or the probability. So in the beginning, uh, I will start with what is a random experiment. So what is random experiment? Random experiment, from there you will see random values will come. So all those things we will just a short definition. What is a random experiment? So in an experiment, so this is an experiment where the result of the experiment, where the result of the experiment which you perform, which is performed or which are performed, which are performed under identical conditions are random, are different. Okay, results are altogether different. Okay, for example, you have, suppose in physics we have an Ohm's law experiment. You give some current into a conductor and you fix the current. Suppose 2 milliampere is the current. Now you will get the voltage. In one case, you will get the voltage as V1. Again, you switch off the entire apparatus. Again, do the same experiment. You will get the V2 for the same current. So, means of course, this V1 will be very close to V2, but that will be different. So these are random experiments. So what happens in those experiments? The outcome of the experiment are altogether different. From here comes another thing, which is nothing but the random value. These are short definitions you might have encountered not many times. So I'm just slowly just giving an idea. So what is this random variable? It is a variable whose value is uncontrollable. Actually, it's unknown and it is not in our control. It is just it can arise. Anything can happen. So that is the situation. So its value is unknown or uncontrollable. Anything which is uncontrollable, which is not in our control, or some dependent variables or something. So these are the random variables. Okay. And generally we define it with a function that assigns, yeah. So functions that assigns values to each of and experiment outcomes, like the heads and tails experiments and all those dice throwing and everything. These are all random experiments. Okay, experiments outcomes. So there are more mathematical definitions of these random experiment and random variables, particularly. So I will not go into the details. Now I will just quickly move on to what is a continuous probability distribution of a probability density function. So PDF, okay. So PDF is nothing but the probability density function. Okay. So probability density function, this PDF, generally written as f x of x. That is, this is nothing but the PDF of a random variable x. This x is the random variable which will assign some value small x. This is some value which the random variable will assign. Okay, this is some value which the x will assign. For example, rainfall. Suppose r is the random variable, which is suppose rainfall. Okay, and it is assigning some value which is suppose 1.1 mm per day. Okay, so this is how we define the probability density function. Okay, on a random variable. Fine. And some basic characteristics. This f x of x has to be greater than equal to 0. Number one. Number two is that it can be higher values which are greater than 1. Okay. So it can be greater than 1 also. Okay. How? Because we know that probability this is actually probability. How we can define probability from the PDF? So for that, suppose you have the distribution or the density function f x of x, and you have x the values of the distribution. So, and suppose you get something like this, some kind of a distribution. Okay. Now you select 2 points, x1 and x2. Okay. These are the 2 points of the random variable, which the random variable will assign. That is some x. This is suppose the random variable. Okay. This x will assign some value, say x1 and x2, in between x1 and x2. So if we need to find the probability of a random variable x in between x1 and x2 will be this area under the curve. So how we can define therefore? Therefore, this probability, that is x1 capital X, which is the random variable. What is the probability that a random variable capital X, this one is the random variable, assigns a value in between x1 and x2, some limit. Okay. So probability that the random variable will assign some value in between x1 and x2 is nothing but given as from x1 to x2 you integrate the distribution or the density function times dA. So this area is represented by this integral. So this is how the probability is defined in terms of probability density function. So this is how the probability density function PDF is and the probability P is related. Therefore, this has to be remembered that PDA, the probability density function, is not equal to probability. This has to be clear. It is the PDF times or the area under the curve of the PDF is nothing but the probability. Fine. So I know that probability. What is the limit? What is the range? It goes from 0 to 1. Right? Probability can be either 0 minimum or maximum is 1. Therefore, now if I replace this with fxx times some delta x, now look at what will be the values of fxx. So this will be 0, no doubt. This is fxx. But if suppose this delta x is a very small number, like in decimal number, fractional number, or fraction, then what will happen? This limit will be always, this limit will be always greater than 1. correct? Because 1 by delta x, if you just divide it, it will be 1 by delta x. So delta x, if it is in decimal, it will be greater than 1. Therefore, fx, there is no limit that it has to be, the maximum limit has to be 1. It can be greater than 1 also. Okay, so this is another thing. Next is the cumulative density function CDA. Okay, next is the cumulative density function. So there is a definition of cumulative density function. Very simple definition. This is written as capital Fx of x. Okay. Similarly, this is capital F is the random variable which assigns some value small x. This is nothing but minus infinity to that value x, probability density function times dx. So it is an integration under the curve of that value and before that. So if this is your distribution, suppose some distribution, whatever, I'm doing it like this. Okay, this is minus infinity, and suppose this is the x. Okay, so the CDA is the area under the curve of this up to this because x. Before that, you just count all the area under the curve of the fxx. That is your this capital Fx, which is CDF, the cumulative density function. Actually, it is defined as probability that the random variable is less than equal to some value smaller. This is how it is defined. So based on this, this definition is absolutely fine. Correct? So this is your TDX. These are basics. You people might know this. So just the basics. Similarly, we will be using expectation value. So just one line definition I will want to give. So expectation value. What is this? Expectation value is defined as of the random variable is minus infinity to infinity x times the probability density function dx. Okay, this is another thing. Okay, one another property I have list called probability density function. So you have minus infinity to infinity fxx dx is always equal to 1 because fxx dx, if you are integrating entirely, that becomes, because this is what this is nothing but the probability. When you integrate it with respect to dx, it becomes probability. Therefore, and probability highest limit will be what? 1. Since you are integrating everything, entire space under the curve, it has to be equal to 1 because the maximum probability. Right. So this is one of the part. Okay. This is the expectation value. Definition of the expectation value mathematically. Okay. Next is another way you can, similar way you can write the expectation value of x square. So it will be nothing but minus infinity to infinity x square fxx dx. Similar definition because it is nothing but the expectation value. Okay, this is one of the things. What about variance of a random variable? Variance of x. Variance of x is actually defined as expectation value of x square minus expectation value of x whole square. This is how the variance is defined. Okay, so this is what the basic uh, things about the distributions. Now I will show you some more distributions and you will be able to understand. Okay, let's go to the some distribution. For example, let us take an example of number one, normal distribution. Very widely used, particularly in this course also we will be using. So this will be normal distribution. Okay, so what is that? Suppose I just make a graph. Okay. So this is your the density function. Let x be the random variable, and here the values which are there, which the x, the random variable, will assign. Okay. So this is how the distribution looks like. In general, the distribution looks like this. Okay. And it is symmetric. Remember, it is symmetric. Symmetric where about x is equal mu. This mu is the population mean. Population mean. Okay, symmetric about the random variable x, which is equal to mean, which is the population mean. So in statistics, what happens is that you have a population parameter, which is a large set, and below in this you have a smaller set of sample. So there is a sample mean and there is a population mean. Similarly, there is a sample variance, there will be population variance. Every time, whatever experiment we do in science, in whatever field, if you do some experiments randomly, those are the samples. Those are not the population parameters. Be careful about that. Okay, but right now we are talking about the population mean of a large number of experiments. When you do that, converges the sample mean converges towards the population mean or population parameter. We will come to it when I talk about the estimators quickly. Okay, just I write the distribution 1 upon root 2 pi given sigma e to the power minus yeah, x minus mu whole square divided by 2 sigma square. So sigma square is nothing but the variance. Remember, this is also the population variance. Remember this. This is population variance. Okay, sigma square is the population variance. Then what is sigma then? This is the population standard deviation. You know, root of variance is standard deviation. Simple. Okay, so this is known. Population mean is also known. So these things are population parameters, and based on which a distribution PDF is created. This is the PDF of this particular distribution. And you can see that x minus mu results into the symmetricity about x is equal to mu. One more thing here is that now, fine. So this is okay. We generally denote it as normal mu and sigma square. This is the distribution. We write it like this. Normal, two parameters are being used, population parameters. One is the mu, the population mean, and another is the population variance. This is how we write because these are the two inputs, mu and sigma. Okay, because x are random, you can vary. Okay, so this is one of the things. Okay, now let's do one another distribution. Next is gamma distribution. Let's go to gamma distribution. Although I don't think we will be using this for today's lecture, but this is important to understand some more distributions. Okay. So gamma distribution is, I'm just writing the distribution, okay, just leave it, not too much important. So this is how it is written, n by 2 minus 1 e to the power minus lambda x divided by gamma n by 2. This gamma is the gamma function. Okay, so gamma of n, you know, this is 0 to infinity. Uh, let us say some e to the power n minus 1 e to the power minus p dt. And here the x should be greater than equal to 0. These are the probability density function of this gamma distribution. This distribution is written as gamma n by 2 and lambda. Okay, you can write n by in place of n by 2, you can change. It can be n also, it can be many things. So based on that, this distribution writing will be different. This gamma n by 2 lambda, when you replace it with some values, it becomes some different distribution. Let me tell you this. If here, if we take n is equal to 1 and lambda is equal to half, then what will happen? It becomes gamma of half comma half. This is nothing but chi-square 1 distribution. You will be using this chi-square 1 distribution. So this is chi-square 1. Okay. So gamma of half comma half. So if you just put it here, n and lambda, you will get chi-square 1 distribution. Okay. Similarly, based on the similar way, if you write gamma of n by 2 comma half, that means in this particular expression, if you just put lambda is equal to half, that becomes your chi-square n distribution. So this is now chi-square n. So this 1, n, these are nothing but the degrees of freedom of the chi-square distribution. Okay. So all are chi-square distribution, but of degrees of freedom n. Okay. So this is another thing which I wanted to show you, and I'm not writing each and everything right now. Another important property is that this chi-square 1 distribution is actually normal 0 1 whole square. Remember, this chi-square distribution, chi-square 1 distribution, is nothing but normal distribution with zero mean, and one standard deviation. Okay, so this is another important thing, that chi-square distribution is related to the normal distribution with zero mean and one standard deviation. Remember, these are all population parameters. Population mean is zero, population standard deviation is one, as I have told you. Okay, square of the normal distribution is chi-square distribution. Okay, so this is another thing. Uh, Let us look at another and last distribution, which I will show you. That is the T distribution, students T distribution or T distribution. I will not write the PDF of this. Just I wanted to show you that how it is generally created. So now, if X is a random variable which is following normal 0 1 distribution, okay, this is following normal 0 1 distribution, and let us say Y, it is following chi-square in distribution. Then your Tn, that is T statistic with means T distribution with n degrees of freedom, will be equal to root n x divided by root y. Fine. So what it will be, therefore, root n normal 0 1 distribution divided by root of chi-square in distribution. This is the T distribution. This is how T distribution can be created. Okay, this is how the T distribution can be created. This is very important. We will be using it while doing the hypothesis testing part. We will be using it. This is also important, that chi-square is normal 0 1 whole square, and other things like this normal distribution. You all know this is uh, generally written. One more thing I remember, which may be helpful. That is, if you have x as some random variable, okay, random variable. So random variable, it will have some distribution. Okay. Now, if I want to know z, which is another random variable, and this z, the random variable z, is a linear function of x. So ax plus b, some a and b are some constants. If z, the random variable, is a linear function of x, another random variable, then the distribution of z is similar or same as distribution of x. What does that mean? If x is a normal distribution, then z will also be a normal distribution. Just remember this. If x is your normal distribution and z is another random variable, which is a linear function of x, the random variable which is having normal distribution, then z will also have the same distribution, that is the normal distribution, but the population parameters might be different. That is the thing. Population parameters might be different based on this linear relationship. Population parameters depend on the linear relationship. Okay, this is another thing which we will be using, relationship. Okay, fine. This is one of the things which I wanted to show. So sometimes what we do, you have normal distribution of mu and sigma square, right? So we write it what? What is this period? 1 upon root 2 pi sigma e to the power minus x minus mu whole square by 2 sigma square, right? This is what your distribution is. What I do is that, let us consider a random variable z, which can be written as this part, x minus mu by sigma. Okay, z is x minus mu by sigma. Fine. This is a linear relationship between z and x, where x is also a random variable, z is also a random variable. Now I know that x, because this is for x, right? Because x is the random variable here. X is assigning that some values. So this is for x. So if x is having normal distribution, then z will be how? What distribution? It will be again normal distribution. But what will be the parameters? Depends on this x minus mu by sigma. How to find it out? Just find out the expectation value of z. Okay, just find out the expectation value of z. What will it be? E of x minus mu by sigma. E of x is what? Expectation value of x is what? Same, the population parameter or population mean, that is nothing but mu minus mu divided by sigma. So this becomes 0. So it will be normal 0. What about variance? I know that variance of z is nothing but 1 by sigma squared variance of x, because mu is a constant quantity. So it will be 1 by sigma square. Variance of x will be again sigma square. So this will be 1. Therefore, if z follows this kind of a function relationship with x, that is x minus mu by sigma, it will be normal distribution, no doubt, based on the previous thing what I have told you. But its parameters can be population parameters can be calculated using expectation values and variance. So what it will be? M01. So just remember this. If x is a normal distribution with some population parameter mu and sigma square, then z, if it is follow this particular distribution x minus mu by sigma, then your z is nothing but normal distributed 0 and 1. Okay, so this is an important result. This we will be using widely in hypothesis testing. Fine. Just remember this. This when you do variance of z, it becomes the constant quantity becomes square. Okay, so it becomes 1 by sigma square. This happens. But you check it using this formula which I have shown of variance, where I have written this. Just try it using this. Okay, you will get it. Fine. So these are the basic distribution and relationship of the distributions. Next, what is the time? 6:30. Fine. Some 12 minutes we can devote, 12 to 13 minutes we can devote here, so that we make up the base for the regression analysis. Next, what I will do is that very important theorem, which is called the central limit theorem. Central limit theorem. What does this theorem states? Let x1, x2, and so on up to xn be identical and independently distributed. Identical and independently distributed. Very important. All these x1, x2, x3 up to xn, these are all random variables and their distribution must be identical but independent. Okay. So if this is the case, then it will have expectation value. So suppose each of them having the expectation value as mu, that is the population parameter mu, and variance sigma square of all is sigma square, the population variance. Then x bar, that is summation, and that's the mean of all the samples up to xn, divided by n, number of uh, observations which you have. This x bar will be having expectation value of what? This will be e of x1 plus e of x2 plus so on up to exn. And we know that each of them have value same, that is mu. So it will be n times mu by n. So e of x bar is mu. Similarly, if you now have to do the variance of x bar, As you know that it is a constant quantity, so it becomes 1 by n square. So it will be variance of x1 plus variance of x2 and so on up to variance of xn. Right? So this becomes 1 by n square and each of them will have value sigma square. Right? So it will be 1 by n square into n sigma square. So n cancel becomes sigma square by n. Therefore, x bar, okay, x bar will have distribution with mu as the mean and sigma square by n as the variance. But what will be the distribution of x bar? See, x bar is related like this, x1 plus x2 plus xn. These are all linearly related, right? So if x1 and x2, all these are distributions, random variables, and they are linearly related. So what we can write? If x is normal distribution, the x bar generally this converges to a normal distribution. The central limit theorem says that if x1, x2 up to xn, these are all random variables which follows identical and independently distributed distribution, then its summation or x bar will be a normal distribution with mu and sigma square by n. This is the central limit theorem's uh, result. Okay, this another thing which you must remember. Okay, fine. So this is I think so. Just what I wanted to show you that this is x1, which follows. Suppose it follows. It can follow any distribution, gamma distribution, normal distribution, uniform distribution, any distribution if it follows. Suppose normal distribution it is following mu and some sigma square. X2 following same mu and sigma square, but different, independent. Okay, and similarly up to xn. Then finally, when you add and divide by n or summation of x is nothing but normal distribution of mu and sigma square by n. This is the central limit theorem's wording. Fine. So this is another thing. Fine. Let me just quickly touch upon estimators as the last preliminary thing. Then we will jump towards the simple linear regression. This is estimators. Okay. So why is it required? Why we require estimators? As I have told you, all those distributions which I have written by far, so far whatever I have written here, all those distributions which I have written, they all require population parameter like population mean, population variance, right? Population variance, remember. But I have already told you that whatever experiment you do, those have samples. Okay, so whatever experiment we do, whatever value which we have, through that we cannot reach towards the population parameter. But we can, through the samples which we have, we can create an estimator kind of a thing so that we can reach towards the population parameter. Okay, let us define and see what I mean. Okay, so let again x1, x2, these are nothing but random samples which you have collected from a data survey or something. Okay, x2 up to xn, the random sample. Okay, random sample from a distribution. I don't know what is the distribution. From a distribution, you have taken some sample with mean, suppose E of xi is theta. Okay, and variance of xi is sigma square. Let us say for time being. Now let's consider let theta cap be an estimator, theta cap be an estimator for population parameter theta. Parameter theta. Whenever you are talking about distribution, whatever it is, its expectation value comes, those are the population parameters. Just remember this. These are population parameters. But what we're now looking for is through the sample we are trying to estimate. Okay. So we define expectation value of this theta cat is equal to theta. If this is true, then this theta cap is an unbiased estimate. I will give you an example that will be clear. So this is an unbiased estimate. If it is not, if E of theta cap is not equal to theta, then theta cap is a biased estimate. Fine. So this is one of the things. Now, let me give you one example. Okay. So let us consider from our random samples, suppose x1, x2, and so on up to xn. These are the samples which we have collected. Okay. And let us consider that this theta 1 cap estimator is suppose x1. This one. This one is the estimator theta 1 cap for population mean. Population mean. Okay. For that, what you require is that I know preliminary things. I already know that x1 is normal, mu, and sigma square. Okay. I know. Let us say that I know. Okay. This is an assumption. Let us say that this sample x1 which we have collected, if you do some 10,000 experiments of the same x1, you will get this kind of a distribution with population mean mu and population variance sigma square. Okay. We need an estimator for the population mean mu. Okay. This is one of the experiments. Now, you say, someone out of you say that no, x1 is not the estimator. Sorry, this theta 1 cap is not equal to x1. I am taking theta 2 cap as x bar. This is a better estimator than x1. Okay. This can be also estimated. I don't know. Okay. So x1 is normal. Let us say that all these x1, x2, and xn, they are all in mu by sigma square. Right? These are the two estimators which I have taken. Okay. Now, now if you look at expectation value of theta 1 cap, which I have chosen as one of my estimators, what it comes? It comes out to be mu. Because why? Because E of x1 is nothing but mu. So it is a unbiased estimator. Similarly, E of theta 2 cap, nothing but E of x bar. And what I know by central limit theorem, if x1, x2 up to xn all follows this normal distribution, then x bar will follow normal, mu, and sigma square by n. So it will also have expectation value of x bar as mu. So both are unbiased estimators. So both are correct. So theta 1 cap can be a possible estimator for mu, and theta 2 cap can be also a possible estimator for mu. But there is a condition to check. We check the mean square error. Through mean square error, you will be able to know wherever the error is less, that is a better estimator for the population parameter. So just let me show you what is MSE represents. It is nothing but, suppose this is theta 1 cap. So it is nothing but variance of theta 1 cap minus theta plus E of theta 1 cap minus theta. Okay. So this theta is a constant because it's a population parameter. So this is constant. So variance of theta is 0. So you have variance of theta 1 cap. And E of theta 1 minus theta is 0 because it's an unbiased estimator. Similarly, MSC of theta 2 cap. What is this? Same by the definition, theta 2 cap minus theta and E of theta 2 cap minus theta. Again, same. Theta 2 cap is also an unbiased estimator. So this is also 0. And this theta is constant. So it becomes variance of theta 2 cap. Right? So what is variance of theta 1 cap? I know from the distribution that variance of theta 1 cap, what I have taken as theta 1 cap, x1. So variance of theta 1 cap is variance of x1. What is that from the distribution? Sigma square. What about variance of theta 2 cap? Variance of x bar, which someone has chosen. I'm just telling you, okay? So this becomes sigma square by n. Now, which one is better estimator? Is it theta 1 cap better estimator or theta 2 cap better estimator? See, this is the variance, which is very high. But this is what? Divided by n. So, of course, sigma square by n is less than sigma square. Therefore, MSE, this is MSE of theta 2 cap. Okay? And this is MSE of theta 1 cap. So MSE of theta 2 cap is actually less than MSE of theta 1 cap. Therefore, theta 2 cap is a better estimated for population mean. Okay. So this is the last concept which I wanted to show you. That so what is this? If you have some sample, suppose 2, 3, 4, 5, whatever, and randomly I've chosen one sample. Okay. Now each of these, suppose the first one, this is x1, this is x2. This x1, under same condition, if you do so many experiments, say suppose 10,000 experiments you do, you will not get 2 every time. You will get 2.2, you will get 2.1, you will get 1.9, and so many. And based on that, I am preliminary assuming that x1 behaves as normal mu sigma square distribution. Similarly, x2 and similarly xn. And by central limit theorem, I know that x bar is same, normal, mu and sigma square by n. What I want, I have only this sample. I don't know anything else. So if you have this sample, based on this you can calculate x bar. How will you calculate? It will be 2 plus 3 plus 4 plus 5 plus 6 divided by 5. Correct? So this you can calculate. Now, x1 also you know. So one person chooses theta 1 cap, one of the estimator for population parameter u as x1. Another have chosen theta 2 cap as x bar. And we have seen that both are unbiased estimator and mean square error of theta 2 cap is less than mean square error of theta 1 cap. Therefore, theta 2 cap is a better estimator for population parameter u. So this is the concept of estimator. Just I am giving you. I will share you these notes. Just try and look for other things also. Okay. So this ends up with what I wanted to show about estimators and all things. Now we will jump towards the simple linear regression and models. Okay. So this will be now simple linear regression. Okay, just so now basic preliminary statistics I have already told you. Different distribution, what is an estimator. So if you have x and z, two random variable with a linear relationship, you have similar distribution, and using expectation value and variance, you can calculate the population parameters. Okay, how to create t-distribution and all, I have already told you. Now, let us go towards the simple linear regression, coming to the week 1 concepts. Okay, so as the simple linear regression model looks like, it says that y is equal to beta naught plus beta 1 x plus epsilon. Epsilon is some kind of an error. Okay, some kind of an error. This is the actual linear regression model called LRM, linear regression model. Okay, this is the linear regression model where beta naught is nothing but the intercept, beta 1 is the slope, and epsilon is some kind of a error distribution, okay, or residual distribution, whatever it is. So it is actually called as the random error component. Fine. Now, what is y? Y is the response variable. Y is the response variable. X is regressor variable. Regressor variable. Now, let me give you one small thing. Suppose this is X and this is Y. Now, I am controlling X. Okay. I am giving value 1, 2, 3, 4, 5. This is in my control. X is in my control. But Y is none of my, it is not under my control. It can be any value. Okay. Let it be 2.1. It can be 2.3. This is 3.2. This is 3.6. And this is 5.2. This is highly random. It is not under my control. So hence it is a random variable. Response variable y is a random variable. However, x is controlled by me, is controllable. Hence, it is not a random variable. Till now, we are calling x as a random variable. Don't confuse it with this linear regression model. Here, x is in my control, hence it is not a random variable. I can choose it. So there is nothing random in it. Okay, this 1, 2, 3, 4, 5, I have assigned. So it's not a random variable. But these are the things. These are not in my control. So it's a random variable. Fine. So this is the basic thing. Okay. So y is a random variable and this random error component, as the name suggests, random. So epsilon, the random error component, is also a random variable. So y is a random variable and epsilon is a random. X, remember, is not a random variable. Okay. So x will not have any distribution. It will not have any expectation values and variance. Okay. Only epsilon and y will have population mean, population standard deviation, and all this. Right? Now, this all this is done. There are some assumptions. Let us write those assumptions because those assumptions will be helpful. So, what are those assumptions? The first one is epsilon I is a random variable, which I have already told you. With now its distribution, we are saying that with zero mean, and sigma square variance, and most of the times it is unknown. Population variance is most of the times unknown. So if the mean is zero and the variance is sigma square, expectation value of epsilon I will be what, therefore? Zero, because zero mean. So expectation value of epsilon I should be zero. Now, what about variance of epsilon I? I know that it is sigma square. Okay, sigma square is the variance of the epsilon I. So variance is sigma square. Clear? So this is one of the assumptions. Second is epsilon I and epsilon j means independent, two independent experiments. So epsilon I and epsilon j are uncorrelated. Why they are uncorrelated? Because they are independent. That's why they are uncorrelated. Okay. So if I is not equal to j, then they are uncorrelated. Third is epsilon I follows normal distribution with zero mean and sigma square as the variance. And these epsilon i's are independent, as I already told you. I is not equal to j and hence it is uncorrelated. Fine. So these are the following assumptions for the random noise component or the random error component. Okay. These are the following assumptions. Now, if I just look for this yi, which is nothing but beta naught plus beta 1 xi plus epsilon. Okay. Now, if I want to do, because this is the linear regression model, LRM is looks like this, correct? Now, E of yi, if I have to write, then what will I do? It will be expectation value of the entire thing, beta naught plus beta 1 xi plus epsilon. Correct? So expectation value of beta is a constant value, so it should come like as it is. Expectation value of beta 1 xi. What it will be? Beta 1 is a constant, but what about xi? Xi here will also a constant because I have told you xi is in my control. It is not a random variable. Therefore, e of xi will remain as it is as xi. Okay, because this is a constant component here. But expectation value of epsilon I is what we have already computed as an assumption. This is 0. This is 0. So you have beta naught plus beta 1, etc. This is the expectation value of yi. Clear? This is the thing. Xi is not a random variable, therefore expectation value of xi is nothing but a constant. So xi will come out. That's all. So expectation value of a constant is nothing but the constant. Fine. So this is the expectation value of the yi. What about variance of yi? Next, variance of yi. Okay. So what is that? So it will be variance of beta naught plus beta 1 xi plus xi. So variance of beta naught plus what it will be? Simple. Variance of beta 1 xi plus variance of epsilon I. Variance of a constant quantity is 0. Right? Because if you have this with time, nothing is changing. It's constant. What will be variance? 0. Right? So variance of beta naught is 0. Variance of beta 1 xi is also 0 because xi is a constant here. It's a random variable. It's not a random variable. That's all. But variance of epsilon I is not 0. What is that? Sigma square. We have already seen as an assumption. Therefore, what we got? E of yi is beta naught plus beta 1 xi. Variance of yi is sigma square. Okay. Now, what will be the distribution of yi? See, I know that epsilon I is a random variable. Okay, epsilon I is a random variable. Let me write it here. Yi is equal to beta naught plus beta 1 xi plus epsilon I. Now I know that epsilon I is a random variable which follows normal distribution with 0 and sigma square. Right? 0 mean and sigma square is the variance. What do you think yi's distribution will be? What will be its distribution? See, this is a linear regression model. It's a linear relation. And xi is not a random variable. So it's a constant kind of a quantity. So if you have a linear relationship, then what I have told you, if one of the random variables is having a particular distribution, say here normal distribution, then what will be the distribution of yi? It will be again a normal distribution. See, the thing which I have told you is being used here. Therefore, epsilon I, which is a random variable and has a linear relationship with yi, epsilon I having normal distribution, yi will also have normal distribution. With, we have calculated expectation value of yi. So with mean as beta naught plus beta 1 xi and variance as sigma square. Right? So yi's distribution is normal distribution with beta naught plus beta 1 xi and sigma square as the variance. Okay, these are all population parameters. Be careful. Now, so what generally people write is this yi is independent because each of the i's will be independent to each other. Independent, and this is normal beta naught with beta 1 xi comma sigma square. Perfect. So this is what how we get. Okay, this is one of the things. Now, so what I do here next is that I make a plot. Okay, so this is your y-axis and this is your x-axis. Understand this plot, you will be able to see that everything is clear. This is x1, this is x2, and okay, suppose xn. some samples we have, and corresponding to that, we have some values like somewhere, let's say here there is one value, and next is suppose here. Okay, these are values, random values, and this is x, which is somewhere here. Okay, so for x1, so these are the data set which you have x1, y1, x2, y2, and xn, y1. So I am just showing this, and this. This is x, this is y. Okay, this is the data set which you have been provided with samples. Now, this is y, this is x. This is, so this is your yn, this is your y2, this is your y1. Clear? Now, what I do is that I fit a line based on this linear regression model. Let us say y is equal to beta naught plus beta 1 x. Okay. So I fit a best fit line. I will show you how you will fit it, how the slopes are calculated and all. Those I will show you. But let us fit a line like this. Suppose this is the best fit line shown by this. Okay. This is the best fit line. Okay. Now at x1, at x1, so suppose this is, that's the y cap I'm writing, okay? So this y cap will be beta naught plus beta 1 x1 for x1, okay? Similarly, y2 cap will be beta naught plus beta 1 x2, sorry, beta 1 x2. So for y1 cap, where is that value? So y1 cap will be this one, right? At x1, wherever the line cuts, so this is your y1 cap. Okay, here at x2, this is your y2 cap. Similarly, here this is your yn cap. Okay, this is the, I know that for the same x1 value, this will follow. Let me change the color. This will follow in normal distribution. I have told you, right? With mean as the beta naught plus beta 1 xi. That is mean as the y1 cap, beta naught plus beta 1 x1 for x1. For x2, here it is the mean. You know that normal distribution, it is symmetric about its mean. So that's why I am putting here, because this value is nothing but this, beta naught plus beta 1 x2. Similarly, for here, it is like this. So this is pure. So what does this mean? Where is this distribution coming from? This x1 is one value. How this distribution comes? So this actually means that if you do some 10,000 experiments, okay, if you do 10,000 experiments fixing the value x1, that is here, you will get different y1. So for first case you get y1, second case you get y1 dash, third case y2 dash, sorry, y1 double dash, and so on. You will get 10,000 values because you are doing 10,000 experiments. Each and every time by fixing the x1 condition, if you do an experiment, you will get so many different values. Okay, from those values, this distribution is created. Understood? Based on those 10,000 values which you have, the distribution is created. What I mean to say is that if you have x1 constant, if you do 10,000 experiments, you will not get y1 every time. You will get some y1 plus delta y. So suppose y1 is 1 here, okay? Sometimes you will get 0.99, sometimes you get 1.01, sometimes you will get 1, sometimes you get 1.02, 0.98, like that way. Similar to 10,000 values if you take and make a distribution PDF, then you will see some distribution like this, where the mean will be given by this. Okay. Similarly, if you fix x2 and do similar 10,000 experiments, and 10,000 is, you can say, a large number of experiments, then you will get this kind of a distribution, normal distribution with mean here, beta naught plus beta 1 x2. Similarly at x. Okay, this is the concept of this particular part. We are saying normal distribution, you have only one sample. Where is the normal distribution you are getting from? So it is the meaning of this is that if you fix one value of x, y you allow it for 1,000, 10,000 times, you get a distribution. And distribution's meaning is given by this. Fine. So this is one of the important concepts. Okay. So now let's go for the quickly for the derivation. Now we call beta naught cap and beta 1 cap are the estimators. Estimators of what? The population parameter, that is beta naught and beta 1. So beta naught and beta 1 in the linear regression model, LRM, these are population parameters. Now I am saying that this is now the estimator for this because we only have samples like this x1, y1, x2, y2. So we only have these samples. We don't have the entire distribution. Okay. So for the samples, you need estimators to go close towards beta naught and beta 1, the actual values. Okay. So now let us go ahead with this. Okay. And you have these samples. Okay. Endpoints are there. Okay. These are the samples. Remember, these are samples. Estimators are only computed for samples to go towards the population parameter. Okay. So this has to be remembered. So suppose this is say x1, this is your x2, this is your x, this is your y axis. So this is your actual y1, sample y1, this is your actual y2. Okay, so now suppose your best fit line comes out to be like this. Okay, this is your fitted line. Okay, this is your fitted line. So what happens is that this is your y1, the actual value, but for the same x1, this is your y1 cap. Estimated value, remember, this is estimated y. Estimated y for x1. Okay, so now this error which you have is E1 is written as Y1, the actual value at x1 minus Y1 hat. This Y1 hat is the estimated value at x1. Clear? Okay. Now, similarly, E2 for all other points I'm not drawing. So it's Y2 minus Y2 cap. Similarly, there are n terms. So you have Yn minus Yn cap. Okay. So now if you do the summation of I going from 1 to n, you will actually get it to be 0. Why? Because there are fluctuations, there are positive errors, there are negative errors. And for a large number of data sets, it will be computed to be equal to 0. Okay. So this is one of the important results. It happens. Okay. Another is that if this is equal to 0, then what we define is that SS residual, which is nothing but the square of the errors, sum of the square of the errors. I is 1 to n. So this is nothing but written as I is equal to again 1 to n yi minus yi square. Okay. So this is the SS residual, sum of the square residual. Okay. So now yi hat can be written as beta naught hat plus beta 1 hat xi. That's all. We will not write epsilon. Why we will not write epsilon? Because this is the estimator. You don't have anything. Okay. This is the estimator. Beta naught cap, beta 1 cap, these are the estimators. Okay. So you do not have any distribution here. Fine. So this is the yi hat. So I will replace. So I will replace this SS residual as summation I is equal to 1 to n yi minus beta naught cap plus beta 1 cap itself, done whole square, right? So finally what you will get is that I is equal to 1 to n. So you have so many terms. So yi minus beta naught cap minus beta 1 cap xi. Remember, xi is not a random variable. Just be careful. Okay, this is good. That's all. This is your SS residual. Now, for best fit, anything best means that for best fit line, we need to minimize the error. Minimize error. So see, the sum of the errors is already zero. So for minimizing the error, we minimize SS residual. And one of the properties of finding out the minima is that you differentiate SS residual with respect to these parameters, the beta naught cap, for that value of beta naught cap, which where it is equal to zero. Similarly, delta S residual divided by delta beta 1 cap for that value of beta 1 cap where it becomes zero. This is the minimum condition. Okay, and based on that, if you do it, you will get simple equations. So I'm just quickly writing. Okay, you can derive it later. You can see the lectures also. It is well derived here. So beta naught cap n minus beta 1 cap summation xi. All summations from I is equal to 1 to n. I'm not writing it here every time. Okay, so this becomes 0. This is the first part. Second is xi yi minus summation beta naught cap xi minus beta 1 cap summation xi square is equal to 0. This is my second equation. Then, based on these, if you solve, you get beta 1 cap as n summation xy. Oh, sorry. Yeah. So beta 1 cap is in summation xi minus summation xi summation yi divided by n of summation xi square minus summation xi whole square, where n is the number of data points or number of sample points. Great. So this is your beta 1 cap. Next is beta naught cap. So beta naught cap can also be found out using, so it is actually, I think, summation yi minus beta 1 cap summation xi divided by all these summations I going from 1 to n. Okay, just remember this. So this is how it is calculated. Now, beta 1 cap and beta naught cap, another way can be written, that is using the mean values. So that is nothing but, that is easier to write. So that is yi minus y bar, xi minus x bar divided by summation xi minus x bar whole square. This summation xi minus x bar whole square is generally written as sxx. Similarly, summation yi minus y bar whole square is written as summation yy. Okay, so just these are generally people can use it. So beta 1 cap, there are two definitions. Either you do go ahead with the summation definition or you go ahead with this. Both are same. Actually, both are same. Similarly, beta naught cap also has a definition, that is y bar minus beta 1 cap x bar. This is again similar to this. Okay, fine. So these are the few things. Now, so we have found out the slope estimator beta 1 cap, and we have found out the intercept estimator beta naught cap. Okay, so finally we can write therefore this y hat is beta naught cap plus beta 1 cap xi. This is now my estimator for y. Okay. So this is another thing. Some properties about this beta naught cap and beta 1 cap, since these are the estimators, we have made this. If you just do the expectation value of beta naught cap, it will come out to be beta, the actual intercept. Okay, the population intercept. Hence, it is an unbiased estimate. Okay, then expectation value of the estimator becomes equal to the actual population parameter. It is nothing but the unbiased estimator. Similarly, expectation value of beta 1 cap is actually beta 1. So this is also an unbiased estimator. Okay, both beta naught cap and beta 1 cap are all unbiased estimators. Next, what? Next is variance of beta naught. Let's do it. Variance of beta naught cap. It actually comes out to be sigma square into 1 upon n plus x bar square by sx. Okay, I'm just writing. You can find the derivation in the lectures. Okay, and variance of beta 1 cap is nothing but sigma square by sx. Remember these two things. We will be using it in doing the hypothesis testing. Okay, so these are the few properties of beta naught and beta 1. So both are the unbiased estimated and both are having this variances. Okay, so this is another thing. Another important property is that expectation value of SS residual divided by n minus 2 is actually sigma square. So this is an unbiased estimation estimated for sigma square, the variance. Okay, and this is written as MS residual, mean square residual. Okay, so MS residual is SS residual divided by n minus 2. So what is SS residual? We have calculated. This is the SS residual, the square of that. So this is nothing but the mean square error. Why? Because it is SS residual divided by n minus 2. So you just look at it. What is SS residual? It is nothing but summation error square. And you have n minus 2, which is you are dividing with the number of samples. Okay. But so this is the mean, this is the sum of the square of the errors divided by the number of samples becomes the mean square error. So this is mean square residual. Okay, so that is how it is defined. It is the mean square residual. That is SS residual divided by n minus 2. Fine. So this is another thing. What else? Uh, yeah. So one of the properties, let us just discuss the properties quickly of least square fit. Then we'll go towards hypothesis testing and questions. Least square fit. Okay, the fit which we have done, the estimated fit. Okay. First thing, summation of Pi is equal to 0. We have already established it. Second, summation of Yi is equal to summation of Yi hat. This is nothing but what? Yi minus Yi hat. So if it is equal to 0, then this will come. Third, SS residual, which is nothing but summation Ei square, which is nothing but Yi minus Yi hat square. This, if you have this, you have summation xi ei. I don't think this is a property. So this is not the property. Let me show you this. So xi ei, this is actually equal to 0. This is one of the properties. Okay, this is the third one. Xi ei summation is equal to 0. And the fourth one is that yi hat ei is equal to 0. So these are the few properties. And you can see that Why is it n minus 2, not n? Is because of these two things. Xi ei is equal to 0 is one of the constants in the ei, the what you call as the residual. This is another constant. So whenever you calculate the degrees of freedom from the number of samples, if you have constraints, you have to subtract it. So if you have n samples and have two constraints like this, that summation ei is 0 and any of them, where xi ei is equal to 0. So these are the two constraints. Therefore, degrees of freedom becomes n minus 2. This is the degrees of freedom. So now the number of samples to which we are dividing is actually the degrees of freedom. Okay. So that's why it is written as this. Fine. Let's now quickly go towards the what you call as the hypothesis part. Before that, one more thing is that this beta 1 cap and beta naught cap, these are all linear combinations of yi. Okay. I am not going to prove it, but let me show you. So beta 1 cap, if you look at this derivation, xi minus x bar, we have calculated this. Yi minus y bar divided by summation xi minus x bar whole square. Okay. Now, the upper part, if you just write, so it becomes what? Yi xi minus x bar, okay, minus summation y bar xi minus x bar. This I can write divided by summation xi minus x bar whole square. Right? So now, if you just open up this part, summation y bar into xi minus summation y bar into x bar, correct? So this thing n times it is just repeating. X bar is a constant, y bar is a constant. So it becomes minus n x bar y bar because there is a summation n times it is repeating. What about this? Y bar can be taken common and summation xi, if you just multiply by n and divide by n, what is now this becoming? N y bar x bar minus n x bar y bar. What is this? 0. Therefore, this part is becoming 0. So beta 1 cap can be therefore written as summation xi minus x bar yi divided by summation xi minus x bar whole square. And I have told you that x's are all taken as a constant part. So I can write this as summation ei yi. So beta 1 cap is a linear combination of y and this ci is nothing but xi minus x bar divided by summation xi minus x bar whole square. Okay, this is your ci. So beta 1 cap can be written as a linear combination of yi. Similarly, beta naught cap. So if you write beta naught cap, what is that? Y bar minus beta 1 cap x bar. I think. Yes. Yeah. So this is one. Okay. Now y bar can be written as summation yi by n. Can be written minus beta 1 cap is nothing but ci yi and into x bar. X bar is a constant. So it is also some c dash I and yi. Okay, so this is beta naught cap and beta 1 cap, both are linear combinations of yi. Remember this. Okay, this is another important thing. Okay, so now I know, I know that yi, its distribution is n of beta naught plus beta 1 xi comma sigma square. We have seen this. Okay, What will be beta 1 cap there? What will be the distribution of beta 1 cap? See, yi is a normal distribution and beta 1 cap is linear combination of yi. Okay, therefore, the distribution of beta 1 cap will be same as distribution of yi. Again, the same rule. But what will be the mean and standard deviation? Very easy. Just write expectation value of beta 1 cap. What is that? We have seen it is beta 1. I've written it down. Okay? In the properties, yes, is beta 1. So, P of beta 1 cap is beta 1 and variance of beta 1 cap is what? Sigma square by SXX. Okay, so we get beta 1 cap as normal distribution of beta 1 comma sigma square upon SXX. Then this is your distribution of beta 1 cap. Fine. Or beta 1 cap can be written as like this. Okay, done. Next. What about beta naught cap? See, that is also normal distribution. Why? Because beta naught cap is also linear combination in yi. So that is also normal distribution. But what will be this? Your mean and standard deviation. Just beta naught cap. I know that is nothing but beta naught. Variance of beta naught cap is somewhat different. So it will be sigma square 1 by n plus x bar square divided by s. Okay. So beta naught cap is normal distribution of beta naught sigma square 1 by n plus x bar square divided by x. That's all. So I know now beta naught's distribution, beta 1 distribution. Now let us do one thing. For hypothesis testing, let us do one thing and then we will quickly solve the numericals. These numericals will not take much time. Okay, so let us move here. Okay, let's start with beta 1 cap. I know distribution is what? N beta no, beta 1 and sigma square by is x. Clear? Now, if I define from z, which is written as beta 1 cap minus beta 1 divided by sigma square by sxx root. Okay, means the root of the variance. This is the standard deviation. Then what will be the distribution of z? Remember this part. Let me go before and show you. Here. Yeah, x is the normal distribution of mu and sigma square, and if z is written as x minus its mean divided by its standard deviation, then z is normal 0, 1. Come back here. It's the same distribution which I have done. Okay, see, z beta 1 cap minus beta 1 and root over sigma square by sx, which is nothing but the standard deviation. You can do root. Now, beta 1 cap is a non-random variable which is having a normal distribution. Therefore, z will be nothing but normal 0, 1. Clear? Now, this is one of the important things. So, z is normal 0, 1, which is this particular quantity. Fine. Now, sometimes what happens is that if I, okay, let us just keep it like this and let us solve one question. Just I want to keep it like this. Okay, let me just do one thing. Beta naught cap. Same thing if we do it beta naught cap, what will happen? Sigma square 1 by n plus x bar square divided by s, right? Similar thing, z beta naught cap minus beta naught divided by, if I do root over sigma square 1 by n plus x bar square by sxx. If I do this, what will be its distribution? Z again is normal zero based on the same logic. Okay. So these are the two things which I keep it here. Now when we solve the question, we will see the hypothesis testing part and finish it. Okay. Now Let us solve now the question. Okay, let's do one. This is, suppose you have been given x and y. Generally, this is what is given in the question. Let us say 1, 2, 3, 4. Okay, and the corresponding experimental value for y is 3, 7, 13, and 21. I have not taken too many samples. It's good to take too many samples. So here the n is 4. Total number of samples is 4. Okay. Let us calculate xi minus x bar. Right. So I'm just writing. We will do it. You will understand. Okay. So let us do what is x bar. X bar is 4 plus 3 is 7 to 9 plus 10. 1 10. So 10 by 4, which is 2.5. What about y bar? 21, 30, 34, 37, 44. So 44 by 4, which is 11. Okay. So let us do one thing. Let us first calculate yi minus y bar and xi minus y separately. Okay. So this comes out to be, I'm just writing here, minus 1.5, minus 0.5. This is 0.5 and this is 1.5. Right. Y I minus y bar minus 8, minus 4, 2 and 10. Okay. So now let us calculate xi minus x bar whole square and yi minus y bar whole square. So what is that? 1.5 square is 2.25. Next, 0.25. Next, 0.25. Next is 2.25. Here, 64, 4 square 16, 4 and 100. Clear? Now, so now what we will do is that let's calculate Sxx. What is this Sxx? Xi minus x bar whole square. Okay. So what is that? Just use sum always. 2.25 plus 0.25 plus 0.25, 2.25. So it comes out to be 5. Okay. Syy. What is that? Yi minus y bar whole square. So what it will be, just add this 64 plus 16, 80, 84 and 184. Done. So these are done. Now what I require another thing is that multiplication of xi minus x bar and yi minus y bar. So I'm just writing it here. Xi minus x bar into yi minus y bar. So the value of this is just you multiply minus 1.5 into minus 8. So that comes out to be 12, 2, 1 and 15. Okay, just multiplication. This into this, 0.5 into 2 and this into this. Okay, so summation xy, which is nothing but summation of xi minus x bar into yi minus y. What does that come? So this will be 30. Clear? So now, can I now calculate beta 1 cap? I think I am. See, this is how it is defined. Xi minus x bar, yi minus y bar divided by summation xi minus x bar whole square. Everything is calculated. Summation xi minus x bar, this is nothing but xy. This is nothing but this x. So what is that? 30 divided by 5. So it comes out to be 6. So beta 1 cap, the estimated slope comes out to be plus 6. What about beta naught cap? Simple, y bar minus beta 1 cap x bar. Y bar we have calculated 11. So 11 minus beta 1 cap is times 2.5. X bar we have also calculated 2.5. Fine. So this comes out to be about minus 4. So beta naught cap is minus 4, beta 1 cap is 6. Therefore, the estimated line y cap is beta naught cap plus beta 1 cap into 6. That comes out to minus 4 plus 6x. This is your best fitted line of these data sets. Okay, this is the best fitted line. Okay, so you now know this. Fine. Now let us quickly calculate what is the EI. So let us again write it further. So this is X, I, and YI. The original question which I have did. 1, 2, 3, 4, and you have 3, 7, 13, 21. Same question, okay? But Y hat now we will calculate. So it will be what? So Y hat will be what? Minus 4 plus 6 into 1. Okay, so that comes out to be 2. Minus 4 plus 6 into 2. 12 minus 4, 8. Minus 4 plus 6 into 3. 18 minus 4, 14. Minus 4 plus 6 into 4. 24 minus 4, 20. So these are the y cap values. Now what is y I minus y cap I? That is nothing but ei, residual. So what is that? 3 minus 2, 1, 7 minus 8, minus 1, 13 minus 14, minus 1, 21 minus 20, 1. Now if you add it, see, sum ei, what it comes out to be? 0. But if you now have to do ei square summation, that is the SS residual, then what will you get? Just square of it, 1, 1, 1, 1. So it will be ei square, that will be 4. Right? So this is SS residual we have calculated to be 4. Okay? Now, one important thing for hypothesis testing. Now we will go towards the hypothesis testing. So what is this hypothesis testing? So now I will change the color again. Now comes the part of hypothesis testing. Same example we will do for hypothesis testing. Hypothesis testing is that we take a null hypothesis H naught where we say that the population parameter beta 1, population slope, for this is for beta 1. Okay? Similarly, we can do it for beta naught. You see that. Null hypothesis is the hypothesis that the population slope is equal to 0. Alternative hypothesis is H1 is the alternative. Alternative. Alternative hypothesis shows that beta 1 is not equal to 0. Okay. In one case, beta 1 is equal to 0. Second case, beta 1 is not equal to 0. Okay. So, what we will do is that generally, sigma square is unknown. Why unknown? Because this is the population parameter. Hence, it is unknown. When something is unknown, you have some samples, you don't know what is sigma square. You have to calculate. We go towards its estimate. And I have already told you that expected value of SS residual divided by n minus 2 is actually sigma square. So this is one of the unbiased estimator for sigma square, right? So this is not also called MS residual. So what we will do is that for sigma square, we will replace it with MS residual. Okay. Now let us write Z is equal to beta 1 cap minus beta 1 divided by root over sigma square by SX. This we have started written. Okay. Somewhere we have written this one. For hypothesis testing, you always go towards this. Okay. And say that this is nothing but normal 0, 1. Great. No problem. Now, we will do some modification here because sigma square is unknown because these are the samples which have been provided to me. So what I will do is that we'll write beta 1 cap minus beta 1 divided by, I just write this as ms residual divided by Si. Just I put it, right? This is what I write. But further, we need to do some changes. See, beta 1 cat minus beta 1. Now, if I do one thing that if I divide it and multiply it by, so root sigma square and divide it by root sigma square, then what will happen? So, beta 1 cat like this divided by root sigma square divided by root over ms residual divided by sxx, right? Ms residual divided by root this times sigma square. Right? Okay, so this will, oh sorry, I'm sorry, this will come. Yes. Okay. So now what we will do next is that this beta 1 cap minus beta 1 upon root sigma square, this is nothing but normal 0. Perfect. There's no problem in this. I think I'm doing something. Uh, yes, just a minute. No, it's okay. Fine. Absolutely fine. Because this root sigma square will come in the denominator of the fine. That is okay. So divided by root over ms residual divided by sigma square. Okay. So this is what we can write. Fine. So now if I just multiply it with n minus 2 and divide it with root over n minus 2, what I get is root over n minus 2 n01 and root over n minus 2 ms residual by sigma square. Right. So this is what we can write. Okay. So now, wait, where is this sxx goes? So sxx will go above here. Just a minute. Just repeat it. One second. It's going to. Okay. From here, let us do it first. Okay. This is fine. Beta 1 cap. This is written, and I have just replaced sigma square with ns residual and multiplied and divided by this. So what I can write now is that beta 1 cap minus beta 1 divided by this I take and this I take. Can I write this? Yes. This divided by root over ms residual and this root sigma square will come in the denominator. That's all. This is what I'm trying to show. Now this is nothing but this normal 0. Okay. This is nothing but normal 0. And now if I multiply n minus 2 root over n minus 2 and root over n minus 2 here. Why am I doing it? I will tell you. So it becomes root of n minus 2 normal 0 1 distribution divided by root over n minus 2 ms residual by sigma square. Okay, this is what you get. Now there is a this ms residual, this thing, the denominator is actually equal to chi square n minus 2 distribution. So this you can see in the lecture notes also. This is actually chi square n minus 2. If time permits, I will show you why it is chi square n minus 2. For the time being, just it is root n minus 2. Therefore, normal 0 1 divided by root over chi square n minus 2. Now, can you tell me what is this distribution? See, in the very beginning, we have seen this. Here, look at it. Isn't it quite similar? Root n n01 divided by chi square n. This is nothing but the t distribution. Okay, this is nothing but the t distribution. So this is nothing but t of degrees of freedom n minus 2. Okay, and this will now be my test statistic. So I will follow now. that test statistic has to be calculated based on this. So what I have is beta 1 cap minus beta 1. So what I have started with, I have started with saying beta 1 cap minus beta 1 divided by this sigma square by SXX. Since sigma square is unknown, we are just putting root over m is residual, okay, divided by S. This is now my test statistic, okay, because we have done some modification here and proved that this Z is nothing but Tn minus 2. So this test statistic is nothing but Tn minus 2. Clear? So now SXX is known, MS residual, you can calculate or I will give you the value. Then you can easily see that what will be uh, the values of the distribution. Okay. So what this statistic is has to be made is that for hypothesis testing, this test statistic has to be understood or has to be calculated based on the null hypothesis SXX at H naught. And what is this H naught? That beta naught, sorry, beta 1 cap is actually equal to, sorry, beta 1 is actually equal to 0. So just put it here. This becomes beta 1 cap divided by root over ms residual divided by s x. This is now actually Tn minus 2 distribution. Now, if in the question it shows that, if in question if we say that you have null hypothesis beta 1 is equal to 0, alternative hypothesis beta 1 is not equal to 0, proves the hypothesis at 5% significance. If this is how the question comes, then you put alpha is equal to 0.05. Remember, this T statistic is a symmetric distribution. It looks something like this. Just like a normal distribution, only it looks, okay, symmetric distribution. So this point will be alpha by 2. This will be alpha by 2. Okay. And this is the area of the alternative hypothesis. This is the area of the alternative hypothesis. And these are the area of the null hypothesis. So if your test statistic this, if when you after calculation comes here, if your test statistic comes here, then you accept null hypothesis, reject alternative hypothesis. But if your test statistic comes here, then you accept H1, reject H0. This is the main concept. So whenever there is something like this, where hypothesis shows that is not equal to 0, see it can be either positive, it can be either negative. We don't know. Therefore, we have to make it alpha by 2, 0.025. Okay. So you have to look for Tn minus 2, 0.025. Whenever you say 5% and you check beta 1 is not equal to 0, just divide it by 2 and check that this is the t statistic distribution. Okay. In our case is 4 because we have 4 samples. Therefore, what will be the distribution? It will be 4 minus 2, 0.025. What is that? T2, 0.025. Now, I have one table. Look at it. Degrees of freedom is 2, correct? And significance level 0.025, not 0.05. Remember, when you have beta 1 is not equal to 0, it can be either positive, it can be either negative. Okay, so you have to take both and equal. So if these two areas they are saying it to be 5%, then it should be 2.5%, it should be 2.5%. That's why 0.025. So it comes out to be corresponding to 2, it comes out to be about 6.205. Right? It will comes out to be about 6.205. Just a minute. Yes. Right. Okay. So this is the thing. I will give you another T test, T statistic thing. But for the time being, it is nothing but 6.205. Okay. So let's go here. So it comes out to be, I think there is something wrong in the tables. I'm just writing it. Uh, it is actually not that. It is actually 4.303. I will give you the actual table. I don't know. I've taken it from the internet. Might be wrong. So it is actually 4.303. Okay. So there is a table. Maybe. So this is the table. Now, what is the test statistic value? Now we have to calculate that. Okay. So beta 1 cap. What is beta 1 cap we have found? Okay. Beta 1 cap is 6 we have found. Okay. What about MS residual? Okay. What is MS residual by the way? MS residual is SS residual divided by n minus 2. What is SS residual? SS residual is 4 divided by 4 minus 2. So it is 4 by 2, which is 2. What is SXX? Which is 5. Just put it. So it is beta 1 cap divided by root over ms residual upon n minus 2. So beta 1, sorry, SXX will be there. Okay, so beta 1 cap is what? 6. Ms residual 2. SXX 5. Based on that, if you calculate, it comes out to be about 9.5. Okay, so now if you just check, this is how it comes, the statistics. This is T2.025, whose value is 4.303. But what is your test statistic? About 9.52. So it comes out in H1 zone. Therefore, reject, you have to reject this H naught, null hypothesis, at 5% significance. That means what? At 95% confidence or 5% significance level, you can say that H1 is true. Okay, H1 is true means beta 1 is significantly not equal to 2. And we know that beta 1 cap we have got as 6. So it is quite relevant. We can see that it is following the pattern. Okay. So this is how the hypothesis testing has to be done. And yeah, some more things which I wanted to show here is that for beta naught also you can do the similar steps. So if you do the last thing, that is the hypothesis testing for beta naught. Okay, there also you can do the same. Z is nothing but beta naught cap minus beta naught divided by root over sigma square 1 by n plus x bar square upon sx. This is how it is written. And this is nothing but normal zero distribution. But sigma square is unknown. Sample when it is given in your question, most of the times sigma square is unknown. So we have to change it. So beta naught cap minus beta naught, and we just replace it again with ms residual 1 by n x bar square by sx. Clear. But this cannot be written as n01 now because ms residual is changed with ms residual. So again we will do something more. So same way beta naught cap. So we multiply by root sigma square, divide by root sigma, and we will write divided by root over sigma square. This part I will take 1 by n plus x bar square upon sx, right? And divided by root over ms residual by sigma square. Again, so this is again z. So z can be written as beta naught cap minus beta naught divided by root over sigma square 1 by n plus x bar square upon sx, right? Divided by, if I now do some root n minus 2, if I multiply and divide it by root n minus 2, so you get ns residual by sigma square. Again, it comes out to be what? Same t statistic, t distribution. So it becomes root n minus 2. The upper part, the numerator is n01, and the lower part is chi square n minus 2 whose root. That is en minus 2 at whatever alpha by 2 level you want it to be. Okay. So now, in the same way, therefore, here the test statistic is this. Ts for beta naught cap is beta naught cap minus beta naught divided by root over ns residual and 1 by n plus x bar square by sx. Clear? So now, if I do the similar way and say that, say beta naught is, so this is your null hypothesis that h naught or beta naught is equal to, let's say, 0, and h1 is that beta naught is not equal to 0. Okay, in that case, what will happen? So your test statistic, as I have told you, it always follows while the hypothesis testing, it will always follow the null hypothesis. Just write the test statistic and proceed. So it will be 1 by n plus x bar square upon sx. Okay, so at null hypothesis, beta naught is 0. So this becomes, oh, it cannot be 0. So I just change it to minus 2. Okay, just minus 2. So it will be minus 2. Beta naught cat is minus 2. Okay, and oh sorry, beta naught cat is, we have already found out as minus 4. That is the intercept. So this becomes minus 4. This can be 0. There's nothing problem. I thought. Okay. So minus 4 divided by ms residual we have calculated just now. What was that? 2, I think. So it is 2 into 1 by n, so 1 by 4. X bar square is 2.5 square divided by 5. So if you do this, calculate this, it will come out to be, just have to see it, it will be like minus 4 by root 3. Something like this will come. Let me calculate. A minute. So it will be minus 4 divided by root 3, right? It will be about minus 2.309. Okay. And I know that T2 of 0.025 I've written is about 4.303. Or, so what it means is that if you just go here, statistic distribution is like this. So this is 4.303. There is another symmetric part which is minus 4.303. This covers 25%, this covers 2.5%, and this covers 2.5%. So this is 0.025 area, this is also 0.025. And these are the H1 part. And this is H naught part. Okay, 4 is minus 4.303, whereas what you get is minus 2.309, which is here. Your test statistic is there, but your t value, statistic value is 4.303. So it comes out, test statistic lies in H naught. So you accept H naught at 5% significance. Okay, so this is how you can continue any question. Fine. So with this, I think we have solved an example and seen how the hypothesis testing test statistic is being created and further how to apply it. Because slope calculation and all these things are easy. You can see that just formula based. So these are the few things. And one more thing is there, but it's already 8. I just wanted to show that this part ms residual by sigma square is actually chi square n minus 2. If I can show that. Just last I will do that and finish it. Okay. So actually what happens is that this EI, the residual error, if you do its expectation value, it comes out to be 0. And if you take its variance, EI, it is actually sigma square. Now, EI by sigma square is happens to be normal 0 1 distribution. Just look into it because if you go to the lecture notes, lectures there in the NPTEL, you will able to understand this. Okay. So now, if I do E square by sigma square, it becomes normal 0 1 whole square, which is nothing but chi square 1. I have already told you normal 0 1 square is chi square 1. Okay. Now, there is a summation, right? E square. So sigma square is a constant, so I can just put it here. Does not matter. So this will be because it is summing from I is equal to 1 to n. It actually we should be chi square n, but since there are constraint like this, so it will be n minus 2 because of these two constraints. Okay, and this can be written as SS residual because that is nothing but the same thing. Okay, that is chi square n minus 2. Right. So what I do is that now, if I multiply with n minus 2 with SS residual and divide by n minus 2, sigma square is also chi square n minus 2 because I have just multiplied and divided. So finally, this thing n minus 2, sorry, this SS residual by n minus 2 we define as ns residual. You have n minus 2, you have sigma square. This is chi square n minus 2. Okay. So just from here it comes. So if you now look into here, see this root of n minus 2 n is residual by sigma square. This is nothing but root over chi square n minus 2. That's all. So this is what you are getting. You are actually getting the root of this. Fine. So with this, I think I should end up here. Right? It's a long discussion because I have started it with. Just give me 2 minutes. I just brief it out what I have shown today. So in the initially, I have just defined what is a random experiment, what is a random variable, just basics of PDF, expectation value and variance. I have shown some distribution which will be widely using the normal distribution, gamma distribution. From there, we define chi-square 1 distribution, t distribution, and we have shown that if there are two random variables linearly related, then the one of the random variables distribution, if it is known, the other random variables distribution is same. And further, we got to central limit theorem. We also discussed about estimators, and then we came to the simple linear regression model. So this is the linear regression model, and we try to look for the properties, assumptions, and finally try to derive the beta naught and beta 1 estimators, that is the slope and the intercept estimators, and finally, based on the properties of the least square fit, we have solved one question and yeah, calculated the beta naught cap and beta 1 cap. We have found out what is the slope and the intercept and hence the best fit line. We have also calculated the SS residual, this one, 4. And then we went to the hypothesis testing where we have tested the hypothesis at 5% significance level. And finally, yes, so these are the few couple of things that necessary modifications required to understand that what causes this to be a t distribution from the normal distribution. So finally, we have seen it for beta naught and beta 1, the test statistics and the hypothesis testing. With this, I will end. Okay. So I will stop sharing here. Thank you. Any question? Okay, if you have any doubts, just come to the next class. I will clear that and then move next class content. The next class content will be short because I have started with some basics, so it went like that. Okay, so I just